When we're solving these systems of differential equations, we can see the linear algebra is going to be useful. So it's going to be useful for us to rewrite these systems in what's called matrix form, so that then we can do some linear algebra with the matrix of coefficients for the differential equation. In particular, find what the eigenvalues of that matrix are. So let's introduce oftentimes when we're talking about vectors, column vectors, we would represent them in bold and matrices in bold to differentiate them from numbers. So just keep that in mind. When you see something bold, that means it is likely a vector or a matrix. So here, this vector x prime is a vector of derivatives. So these would be the derivatives of x1, x2. If we have three variables, dependent variables in our system, then it could be three different derivatives. So what's nice about these methods that we're going to talk about are they scale up very easily for systems of 3, 4, 5, 6 differential equations. So if I want to write this in matrix form like this, where I have a vector of derivatives is equal to some matrix of coefficients times a vector of x values. So for the first one, my matrix would be x1 prime, x2 prime, x3 prime. So I'm going to use primes instead of the dx dt notation. And that's going to equal some matrix A, should be a 3 by 3 matrix, times x1, x2, x3. So over here is our matrix X, and over here is this vector we're calling x prime. And in the middle, this matrix A, what we're going to do is pull off the top row of this matrix is going to correspond to the coefficients in front of the dx1 dx1 dt equation up here. So in other words, I'm going to pull off the 4 in front of the x1, the 7 in front of the x2, and the -1 in front of the x3. And now you can check that if I were to multiply this times this, I would get 4x1 plus 7x2 minus x3 equals x1 prime. And we do that for the other equations too. We just need to be careful that we get things in the right order. So the first entry here would be the coefficient in front of the x1, which is -2. We have no x2 in that second equation, and we have a -11 x3. And in the very last equation for dx3 dt, we have no x1 term, we have a -1 in front of the x2, and we have an 8 in front of the x3. So usually these terms are lined up in the right order. I jumbled them up a little bit just to make you aware that you should be careful, that you don't just assume they're in order. So here's our matrix A of coefficients corresponding to this system of linear differential equations. And coming over to this one over here, we could do the same idea. We have our vector x prime, which would just be x prime, y prime, z prime. That's going to equal some matrix times x, y, and z. Those were our variables. And now we would just pick off, well, what's the piece in front of the x? So that would be cosine of 2t, 0, sine of 2t, and then we have 0, e to the t, 0, and we have sine of 2t, 0, cosine of 2t. And that would give us a way of expressing this system of differential equations in matrix form. So we don't need constant coefficients in front of the x, y, and the z, for example, in order to apply our methods. So we're looking at cases where all of the terms in front of our variables are going to be constant coefficients. But let me just say you can generalize this process that we're going to talk about to handle linear systems where the coefficients might depend on t, so they might not be autonomous. So that's a nice advantage of using this linear algebra method. It scales up to much higher dimensions pretty nicely.